In this video, I'm going to talk about applying restricted Boltzmann machines to collaborative filtering. Collaborative filtering means trying to figure out how much a user would like one product based on how much that user liked other products and how much many other users like products. The particular case we'll look at is the Netflix competition, in which a machine learning algorithm has to predict how much a particular user will like a particular movie. The training data for this competition consists of 100 million ratings of 18,000 movies by 500,000 users. So it's quite a big data set. It's not the kind of thing anybody at the time imagined a Boltzmann machine could deal with. As we'll see, there's an important trick to being able to get a restricted Boltzmann machine to cope with the fact that nearly all the ratings of nearly all the movies are missing. But when we use this trick, we're able to train models that are very useful in practice and were in fact used in the winning entry. So now I'm going to explain how restricted Boltzmann machines were used for collaborative filtering in the Netflix competition. In that competition, you're given most of the ratings that 500,000 users gave to 18,000 movies, and each movie gets rated on a scale from 1 to 5. Each user, of course, only rates a small fraction of the movies, but even so, there's about 100 million ratings, so it's quite a big data set. You have to predict the ratings that the users gave to held-out movies, and if you can do that well, you get a big prize. You actually win $1 million if you're the best person at doing that. So you can draw the ratings in a big matrix like this, where we have movies across the top and users down the side. And so, for example, user 2 gave a rating of 5 to movie 1 and a rating of 1 to movie 3. User 4 gave a rating of 4 to movie 1, and the question is, what rating did he give to movie 3? You might decide he's quite like user 2 because he rated movie 1 the same way, so maybe like user 2 he hated movie 3. On the other hand, user 4 liked movie 6, so maybe he likes all the movies. By the time you've done that much reasoning, you realise you better use some statistics. Let's start by trying to use a language model. It sounds bizarre, but as you'll see, it's equivalent to a standard method. So we can write the data as a string of triples, much like the family trees. Each triple has the form user, movie, and rating. So here's some of the data from that table on the previous slide. And we just have to predict the third term of a triple. So if we built a language model, what we would do is we'd convert each user into a vector of features for that user, that is, a vector that we learned, and we convert each movie into a vector of features for that movie, a vector that we learned, and from those two feature vectors we'd try and predict the rating. Now, the obvious way to do this is to put in a big hidden layer and make the feature vectors feed into the hidden layer and then have the hidden layer predict the rating. We tried that, and we couldn't get that to work any better than a very simple method, which is simply to take the scalar product of the feature vector for the user and the feature vector for the movie. You just multiply them together pointwise, add it up, and output that as your rating. So it's not even a softmax. You actually output whatever real number you get from the scalar product. Now that's exactly equivalent to doing something else, which is normally called a matrix factorization model. If we arrange the user features down the rows and the movie features above the columns, we can see that if we multiply that matrix of users times features by the matrix of features times movies, then we'll get predictions for the ratings, and it will be exactly equivalent to the language model that's beside it. So the matrix factorization model is the most commonly used model for collaborative filtering like this, and it works pretty well. Now let's consider an alternative model using a restricted Boltzmann machine. It's not obvious how you would apply a restricted Boltzmann machine to this problem, and so we had to do some thinking. In the end, we decided that we'd treat each user as a training case. And so a user is really a vector of movie ratings, and for each movie we would have a visible unit that had 5 alternative values. So the visible units, instead of being binary, are 5-way softmaxes. And so the network, or the restricted Boltzmann machine, looks like this. Each of its visible units is a 5-way softmax, with 1 visible unit per movie. You might start worrying about there being 18,000 visible units here. And then we had about 100 binary hidden units. And each hidden unit is connected to all 5 values of the softmax. It also has a bias. And so you can see the number of parameters we'll have is large. The CD learning rule for a softmax, incidentally, is exactly the same as for a binary unit. And like I said, we've got about 100 hidden units. And what we're going to do is learn a model and then try and fill in one of the missing values using the model. Now the problem with this approach is we don't want to have an RBM with 18,000 visible units, only a few of which have known values. That's a huge number of missing values to be dealing with. And there's a neat way around that. For each user we use an RBM that only has as many visible units as the movies that the user rated. So it's possible that every user will correspond to a different RBM with a different subset of the visible units. Now, all of these RBMs are going to share the same weights. That is, we know which movie is which, and so if 2 users saw the same movie and rated the same movie, the weights from that movie to the hidden units will be the same for those 2 users. So we're doing an awful lot of weight sharing here. And that's lucky, because for each user we only get 1 training case. We make this specific RBM for each user with the right architecture, that is the right number of visible units for the movies that the user rated. And now there's only 1 training case, which is that rating vector. But all of these 500,000 training cases share weights to hidden units, and so the learning works fine. The models are trained with CD1, and then after a while with CD3. That is, you go up and down 3 times before you collect the statistics for the negative phase, and then with CD5, and then with CD9. And how well does it work? Well, the RBMs work about as well as the matrix factorization methods, but they give very different errors. What that means is that if you average the predictions of the RBMs with the predictions of the matrix factorization methods, you get a big win. And the winning group actually used multiple different RBM models in their average, and multiple different matrix factorization models, and I think probably other models as well. As far as I know, their main models were matrix factorization models and RBM models.